chances are you've used some kind of text search engine. Maybe it's a chatbot, maybe it's Google, but basically you're supplying a text query and you're getting text results. But what about supplying a text query and getting image results? Or even supplying an image query and getting text results, or image query and getting image results? Image understanding is the next evolution of semantic search, where we can actually capture the images of a data set and encode them in order to do similar semantic search as if we had a text corpus. And so what we're going to do is dive into how vision encoding models work, and we'll walk through some examples, some real live examples of applications that are powered by this sort of technology. So let's dive into it. So think of image understanding as no different than text understanding, where we are using, instead of a BERT model, a text-based BERT model, we're using some kind of vision transformer model. And if you've heard of CLIP, CLIP was published by OpenAI. It's an open source model that actually, what it does under the hood is when you supply it an image, typically some kind of base 64 string of an image, it converts that image into a number of patches. We call these squares, or we call these patches, but they're effectively just a bunch of squares that have been cut out from the image. So for example, if we have some kind of image, we convert that image into 16 by 16 squares, right? And so what we then do is we have all of those converted into vectors, and then typically they are averaged together, they're mean pooled into a single embedding. That's a very rudimentary approach in capturing the embedding of an image, but for example's sake, this is how we can expect it working under the hood. So again, we supplied an image, any kind of resolution, we convert that image into patches, we then use some kind of transformer architecture to convert those patches into a fixed dimension embedding, typically 768, 1024, etc. And so what that allows us to do is capture the actual contents of the image and encode those contents into an embedding, right? And so that allows us to say, hey, let's say we have an image of red sneakers, we can convert that red sneaker image into a fixed array of high dimensional floats, right? And so what that does is, depending on the embedding model that we use, it's able to understand, hey, this position of this point in this multi-dimensional array is associated with the color red, it's associated with a sneaker, it's associated with a certain type of aesthetic, maybe a style. And so all of these have been trained into the transformer architecture for this model. And so we use different types of embedding models in order to support different types of image understanding. So for example, if we have a very basic product image, maybe we want to use a CLIP embedding model. If we have, let's say, a diagnostic image, right, maybe a medical asset, and we want to use some kind of CLIP model, maybe that's fine-tuned for X-rays, right? So again, CLIP is the most common model that people typically use. What we'll walk through is CLIP and a CLIP derivative called SIGLIP that Google actually published. And so on this left-hand side, again, we can encode an image into an array of floats, but we can also encode a text into an array of floats. And so this gives us the ability of doing not only image-based queries on an image data set, but also text-based queries on an image data set. And so because these share the same embedding space, we can do search across all of these different modalities. And this is at its core. When people say multimodal, CLIP is often what they think of. But it's not just embeddings that we're able to capture from these types of models. We can do what's called object detection. And some of the more popular models under the hood are YOLO-based models. YOLO stands for you only look once, and it's a really common way to do high performance, high frame rate image recognition or object recognition across a known data set. And so in this case, we have a data set that we're using to train. We have the training epochs, image size, etc. And so that then gives us the ability to detect objects, to do segmentation. So we talk about SAM2, SAM3 in a different video, to do classification, right? Given this image, what category does this image fall within? We've got pose detection, et cetera, et cetera. And so YOLO is a very common foundational training architecture to do these types of downstream object detection and image recognition tasks. And so you can think of them as object detection, scene understanding, et cetera. And so there's a ton of models on the Hugging Face directory that are really good at, let's say, certain types of tasks. So we can do image classification, right? So We could do not safe for work image detection. So if you want to actually flag images that shouldn't be in a certain corpus. Let's see if we wanted to sort by most downloads, age image detection. So these are all different image models. Some of them are transformers, not much different than clip. Some of them are YOLO based object. So yeah, here is a YOLO based object detection model, or maybe not. But yeah, so some of these models are transformers, some of these are YOLO based, etc. And so once we have these models in a serving architecture, then again, we can supply an image, we can get the embedding, we can get just a bunch of tags. So the tags are just labels that are pulled from models like YOLO, etc. And so then we have the ability to do, again, this cross-modal search where we're supplying some kind of text as an input, we're encoding that text, and then we're using the encoded text as a query to do a cosine similarity, a k-nearest neighbor, to find across our corpus of image embeddings what is the most similar. And so we can supply a text query, we can supply an image query, we can combine text plus image query in order to find from our image corpus what is most relevant, the matching images. And so let's actually walk through what that looks like. If you were using a vector database like Quadrant, Pinecone, Weaviate, Mongo, Postgres, they all support the ability to define your vector configuration up front for the index that you're going to be using. And when you do that, you actually have to supply the fixed dimensional length of the index that you're using. This is really important because different embedding models are associated with different sizes, right? So for example, we have an image extractor embedding. So under the hood, this is probably using SIGLIP, but with Mixpeak, we actually abstract the models and the dimensions, etc., so that you just think about the feature extractor that you're using. And so in this case, the image extractor embedding is using 768 dimensions. All of these different models or all of these different feature extractors are powered by different models. And as you can see, all of them have different dimensions. And so this can get kind of challenging because you have all of these different dimensions, you have all of these different models. What happens when you have a different model where you fine tune a model, you have to re-embed all of your existing points. So that's a topic for a different discussion. And so this is the Mixpeak Studio. And in this example, I have 118,000-ish images that I've ran through the image extractor, feature extractor. We have this feature URI that we're using. This feature URI is important because it allows us to do retrieval on the image embedding that we've pulled out using the image extractor. And in this case, we're using the Google SIGLIP model. And if we look at the Hugging Face, we could see Google SIGLIP. Forget which actual SIGLIP model we're using, but it's important to note the SIGLIP model that you're using or the image embedding, or really any kind of encoder model that we're using, because the different patches, the different dimensions, the different frozen weights all correspond to one fixed latent space. And so it's important to pin that association when you do retrieval, when you do feature extraction, etc. And so in this case, we're probably using SIGLIP, some kind of derivation of SIGLIP there. And so we have that feature URI, 768 dimension. And so we have that feature URI. And now if we look at our collection, we have the number of documents are associated with the number of objects that we've processed through the feature extractor. So if we take a look at one of these here, we've got the image, and if we go down to some of the extracted values, some of these are internal fields, some of these are user supplied fields, but then we have the fixed dimension array that we're using to do the k-nearest neighbor operation, the image to text, text to image, etc. search. And this is a 768 dimension array of floats that corresponds to that SIGLIP model under the hood. And so let's look at an actual retriever operation. And so what we'll do is let's create a retriever. So we'll call this test gallery search, and we will use the gallery collection. And if we take a look at the gallery collection, we already know what feature URIs we have available because each collection is tied to a particular feature extractor. And we can see the feature extractor has inputs. That's not as relevant for the retrieval side of things, but what's important actually to note is the output schema of the feature extractor, because that is what allows us to do retrieval on different fields in our collection. And so then what we can do here is we can do a text query, but we can also do an image query. Right? And so we'll walk through, in this case, just this basic text query. And then we also have a published retriever that supports text, image, and document reference as an input for a retrieval operation. And so this is just a subset of 10 documents from our collection, which is good because it gives us the ability seeing what our retrieval operation is doing under the hood. And so in this case, we have the siglip model, and we can do dogs outside and run that query. Each.find is not a function. Let's look at an existing retriever here. So we say dogs outside, boom. And so we get our results, right? So the dogs outside query is encoded into the same semantic space, in the same latent space as the documents that we processed in this collection. And so we can see, okay, these are the different results. Each of these have different scores, right? That is the relevance score for the result for the query that we're running. And in this case, we have the ability to do a text-based query. We have the ability to do an image-based query, or we have the ability to do a document reference-based query. And so this gives us the ability of saying, hey, given this result, right, this document in this case, use that as a query to find similar documents. And under the hood, what we can see is what the actual query in this case looks like. And so we have a single feature search that is potentially running under the hood, three different modality-based searches. In this case, it's taken the input from the text, it's taken the input from the image, or it's taken the input from the document. It can be or it can be and, right? So we can supply all of these at once when we run the retriever operation, and it combines them all into a single embedding in order to do that k-nearest neighbor feature search operation. And so let's take a look at what this published retriever page could look like. This is a live demo. You can check out the page here. It's mxp.co/r/nga. NGA stands for the National Gallery of Art. And they just have a public archive of a bunch of different images as portraits that we've ran through the Mixpeak image extractor. And so in this case, what we can do is search 18th century oil portraits, right? And so we have all of these images down here. We can click this magnifying glass, and that gives us the ability of doing a document reference search. And this document reference search is actually combined with this text query, right? And so it's saying, hey, given this 18th century oil portraits plus this Elizabeth Fulford Welshman document query, combine them in order to get results that have that combination of results. So let's clear this. We do again, dog outside, get that. We got all the results. And then what we can do is actually supply an image, right? So I have a picture of an Australian Shepherd. We can use that as a reference or as a in our search query to say, hey, given this image plus dog outside, do that search query, right? And what it's doing under the hood is it's actually combining the text query with the image query. It's mean pooling them together, right? It's taking the average of these two embeddings and then using that to do the retrieval operation. And because these are using the same feature URI, we don't need to do any hybrid search reciprocal rank fusion in order to do the actual feature search. And we talk about reciprocal rank fusion and hybrid search in a different video in the Mixpeak University module set. And so in this case, again, we have that image query plus the text query in order to get the results. And so again, we can combine all three, text query, image query, plus document reference in order to get the results that we want. And so when people say image understanding, image search, multimodal search, this is what they mean. We are supplying a text query. We are combining that text query with an image query, and we are taking those combinations of embeddings and then using that in order to generate a query that traverses our image corpus, our image index. And so this gives us the ability of doing image search across a image data set. And you can see this example if you go to mixpeak.com/showcase. It's at the top. If you look at resources, there's a showcase page, and we have this live demo that's linkable from the mixpeak.com/showcase website. And so again, my name is Ethan. This was the image understanding walkthrough, and we just walked through end to end the actual ability to use an image embedding model off the shelf, use an image classification, image detection, object detection model off the shelf in order to create an index that can support text-based queries, image-based queries, document reference-based queries, and any combination of all three of them in order to get the most relevant results for the query, for the access pattern that users have. Thank you so much for following along, and I'll tune into the next one. Thanks.